this beyond just one predictor. So we can have p predictors, in fact, so from beta 0 all the way to beta p, and we're still going to end up with this same equation, x transpose x inverse x transpose y. And so what do you think the dimensions are of the design matrix X now? So now X is going to be an n by p plus 1 matrix. And so before, this was just n by 2 because we just had beta 0 and beta 1. But now we've got p predictors, and so we end up with an n by p by 2 plus p plus 1 matrix because we have p predictors plus 1 for the intercept. And so this is what that looks like. We've still got that column of 1s at the front, and then we have each of the x values. Each column corresponds to a different x variable or a different x predictor, and each row still corresponds to a different observation. Okay, so now let's talk about interpretation. So what is the interpretation of beta hat in multiple linear regression? So the coefficient for x is beta hat, and you always want to give the confidence intervals for that, so the lower bound of beta hat and the upper bound of beta hat. And what this means is that a 1 unit increase in x yields an expected increase in y of beta hat, holding all other variables constant. This is really an important, I'm going to say this one more time because this is very important to understand this interpretation of beta hat. So a 1 unit increase in x, a 1 unit increase in our predictor, yields an expected increase in y of beta hat, holding all other variables constant. So the types of questions that we ask with linear regression is there a relationship between a response variable and predictors? How strong is that relationship? What is the uncertainty? How accurately can we predict a future outcome? And so this beta coefficient that we've been talking about is what gets at whether there's a relationship between a response variable and the predictors. And so then we have to actually get at how strong the relationship is and what is the uncertainty. So the standard error of an estimator reflects how it varies under repeated sampling. And so the variance of beta hat is going to be equal to sigma squared. And so if you remember, that's going to be that variance of the error times x transpose x inverse. So sigma squared, again, is the variance of the error term. And in the case of simple linear regression, the standard error of beta hat 1, and so that's going to be just the slope, that's going to be, or the standard error squared, so this is the variance of the slope, is going to be equal to sigma squared divided by the sum of xi minus x bar squared. And this uncertainty here is used in the test statistic t, and so that's what we use to sort of think about how large these effects are. And so t, that test statistic in simple linear regression, is going to be equal to beta hat 1 divided by the standard error of beta hat 1. We're going to cover more aspects of this in the next class.